At things a little bit more closely. How are we feeling vis-a-vis chapter 5? The 5-3 FRQs? Okay. Do you want to do some stuff here to start? Some review stuff? Walk through how to do some things again? Helpful? Okay. Where would you like to start? Elena. So you're looking at this one here. Okay. There you are. Okay. It says the graph of the function f consisting of 3 line segments is given above by the integral from 1 to x of f of t dt. Compute g of 4 and then g of negative 2. So g of 4 is going to be the integral from 1 to 4 f of t dt. So it's like gonna be like this shaded area, right? So when I look at this, I'm gonna think about it as a trapezoid and then like a triangle. So I'm going to compute the area for that trapezoid and then the area for that triangle. Or you could break that trapezoid up into like a rectangle and a triangle and add them together, whatever. Either is fine. You can get the same result. So the area for a trapezoid is 1/2 the height of, or the average height of the bases. So our first base has height 4 and our second base has height 1. And then the height of the trapezoid is just that distance, which is 1. And then I have plus the area for that triangle, which is 1/2 base times height. The base and height are both 1. Oh, yeah, thank you. I guess I missed that. Yep, it's a 4. So I noticed that this triangle, that triangle are the same. One is above the x-axis and the other is below, so they're just going to cancel each other out and make it 0. Thanks, Finn. So we have like, you know, one of those and bloop bloop. So we just end up with 5/2. Feels okay. And then we have g of negative 2. So that's the integral from 1 to negative 2 f of t dt. So the first thing I'm going to do is I notice that the bounds of my integral go from big to small rather than from small to big. So I'm going to flip those. Yes? So there's a negative on top. Well, if the smaller number is on the top, I would flip it. I mean, if it went from negative 3 to negative 2, that's appropriate, even though there's a negative number on top, because it's going from small to big. But that's in general what I'm going to try to do. So far, so good? Okay. So what I'm doing then is I'm integrating from negative 2 up to 1, which is just that triangle there. So the height of that triangle is 4, and the base of that triangle is 1, 2, 3. So we have negative 1/2 4 times 3, so that's negative 6. Feel good? Okay, so that's part A. Let's erase some of that stuff now. Part B, it says, find the instantaneous rate of change of g with respect to x at x equals 1. When I hear instantaneous rate of change, I think derivative. And since it's at 1, I'm going to be looking at g prime of 1. Now I'm going to compute g prime of x in general first, and then we'll do g prime of 1 afterwards. So g prime of x is going to be the derivative of the integral from 1 to x f of t dt. Well, that's just going to be f of x times the derivative of x, or just f of x. So g prime of 1 is just going to be f of 1. So if I go to my graph and I find where x equals 1, f of 1 is 4. Still doing good? Okay. Part C says find the absolute minimum value of g on the closed interval -2 to 4. Justify our answer. So if I'm looking for an absolute minimum or maximum, I need to consider where the derivative of g is equal to 0 or where it's undefined. Or the endpoints. Everybody's okay there? Elaine, are you okay? So I need the endpoints because they ask for an absolute maximum or minimum. If it was just a local or relative max or min, I do not need to include the endpoints. So let's first remember that the derivative of g is just f of x. So if I go back to my graph, if I look, where is the derivative of f, or where is f equal to 0? At 3, right? So I'll include that as a point to check then. And if I go and look at where f does not exist, or where it would be undefined, there's nothing, right? Because it's a continuous function. Everything is connected together. Nate? If I was looking for concavity and I had to consider the derivative of f, then the derivative of f would fail to exist at 1 because it's a corner. But f is just that function that's we're drawn, right? We're talking about the derivative of g, which is f. So f is continuous everywhere. Does that, you feel good? Elena, does that? Okay. So we have 3 values to check then. So g of -2. Thankfully, we've done that already, right? We did that in part A. That was -6. And then g of 4, oh, we did that already in part A. That was 5/2. And then we need to check g of 3 and see which one of these 3 is going to be the smallest. So g of 3 is the integral from 1 to 3 of f of, or I should say f of t dt. So far, so good. So if I go back to my picture, that's going to be, oops, don't do that, please. So from 1 to 3 is that region there. So that's going to be the area of that trapezoid. what was that? 1. And then that other little triangle. So that comes out to be 3. Of those, my local minimum is, or my absolute minimum has to be at -2, because that's the smallest value. I'll just read that question one more time. Okay, so we'd say that the absolute minimum value there is -6. And this is using like the second derivative test on a closed interval. If you wrote that as your justification, that would be plenty. With this work that we've shown, definitely adequate. So when it says justify your answer, like, you don't have to, I mean, I think you'd be fine even if you didn't write, you did the second derivative or the first derivative test on a closed interval. But like, that's what we did there. So far, so good, Elena? And then the last part is D. It says the second derivative of g is not defined at x equals 1 and x equals 2. How many of these values are x coordinates of points of inflection of the graph of g? Justify your answer. So it tells us that these two are places where the second derivative of g doesn't exist. And that should be obvious, Nate. That's what we just talked about a moment ago, because that's where f has a corner, because the second derivative of g is the first derivative of f, and we know the derivative doesn't exist at a corner. So first thing I would do is observe that the second derivative of g is the first derivative of f. And at x equals 1, if I go look at f, if I look at f here, to the left of 1, f has a positive slope. To the right of 1, f has a negative slope. So the derivative of f is positive when x is less than 1, and it's negative when x is greater than 1. What I'm observing there is that my derivative, or my second derivative of g, changes signs at x equals 1. That is the definition of an inflection point, is that the second derivative changes signs at that value.
So it'll just be x equals 1. It's x equals 2.
Yeah, that's exactly what I would be writing. So we have positive, negative, negative. So we'd say x equals 1 is RIP. So if I draw my little sign diagram, this is like my concavity test here. So I'm just looking at the first derivative of f or the second derivative of g. They mean the same thing in this problem. Elena, does that feel good as to how we did that? And notice that there wasn't a ton of computation in a lot of these places, right? It really was testing to make sure that conceptually you understand like how to use these concavity or min and max tests. And you can do it whether it's moving from symbolically to graphs and being able to use those interchangeably, which is tough, right? Until you've kind of gotten some practice at it. But like, as you talk through it, it's like, okay, I see that there's not like, I'm not missing anything by not really having any calculation to show, right? And a lot of these, it's just looking at the picture and going, oh, okay. And like, you could calculate a slope, like the second derivative of g for these values, but like, seems like a tremendous overkill to me. I'm just going to look at the picture and note the slope of f, which is going to be plenty for me. you know, calculate those slopes if you wanted to, but like, I don't think it's adding any insight, getting the actual number versus just observing that it's changing sign from positive to negative, which I can do with my eyeballs. Give my calculator a break on that. Does that feel a little bit better? So I think an excellent explanation would just provide the sign diagram. You know, like I think that is wonderful amount of thorough explanation where you've given me like, okay, I'm considering these two inflection points. Here's the sign of the second derivative of g on those intervals. I can see there's a sign change at 1, but not a sign change at 2. You know, that would be good, I think. Does that feel okay? And I think more often than not, like when we say justify, we're not looking for a paragraph. You could write a paragraph and do it, that's fine. But usually what they just mean is like, you got to show some work here. Use calculus to back up how you reached the conclusion. Because you probably could look at this and go, okay, yeah, it's got to be, you know, it's got to be this one rather than this one, just by looking at the picture. But they don't want that. They wanted you to explain how you got there. Or justify how you got there. So like, oh yeah, I'm sure that you didn't just guess. This is the only, because the way the question is structured, it's like I could just say x equals 1 and just guess and maybe I get it right. The justification piece is ensuring that like you had a good reason for guessing x equals 1 rather than just being like, I flipped a coin, you know, figured it's going to be one of the two but not both. I just picked that one. Alex. Yeah, sure. Well, that took more than I wanted it to. All right. So it says the functions f and g are given by yada, yada, yada. It says it says find f prime of x. I think there's a little prime symbol there. And then g prime of x. So f prime of x is going to be the derivative of this integral. So again, using the fundamental theorem of calculus part 1, I'm going to get the function inside just with the bound replacing it, and then times the derivative of that bound. Oops, come on now. Who said that? I just trying to move over. So I'm going to get derivative of 3x is just 3. And then I have the square root of 4 plus 9x squared. Does that feel good there? And then part B, g prime of x is going to be the derivative of f of sine x, which is going to be f prime of sine x times the derivative of sine x, right? That's a chain rule derivative. So we have f prime, right? That's 3 and then 4 plus 9, and then we're going to plug in the sine in for x. So now I have sine squared in there. And then times the derivative of sine is cosine. Does that feel good? Any questions on what I did there? There's some like nested chain rules going on, which makes it kind of confusing. But if you do it, if you got f right, and you don't try to do this composition first and then do the derivative. If you just do the derivative with f of sine x, it's a lot cleaner as to how you apply the chain rule there, right? If you tried to plug the sine into your answer up above, it's kind of a mess. Oops, that's all part A. Part B says write an equation for the line tangent to the graph of y equals g of x at x equals pi. So to do that, we're going to need the point pi comma g of pi, and then we need the slope at, and that's going to come from the derivative evaluated at pi. Feel good? Okay. So if I do g of pi first, that's going to be f of sine of pi. Sine of pi is 0, which means that's going to be the integral from 0 to 3 times 0 of 4 plus t squared dt. There is. If I integrate from 0 to 0, that's just 0. The upper and lower bound are the same. The integral is, by definition, going to be 0 because the shape you have is just a straight line. The area of that is going to be 0 because it's a one-dimensional figure. So we have the point then pi 0. So that's going to be the point. Next thing we need is the slope. We're going to get that from g prime of pi. And I know g prime of pi is 3 times the square root 4 plus 9 sine of pi squared times cosine pi. Is everybody okay with where I plugged that? Okay. And we said the sine of pi was 0. So that's going to just be 3 times the square root of 4, which is just 2. And the cosine of pi is -1. So pi is 180 degrees, so you're on the left side, so it is -1. Remember, cosine is the x. So that's -1. So that's -6 then. So if we just use our point slope equation for a line, we can say y minus 0 is equal to -6 x minus pi. So y equals -6x plus 6 pi. Alex, does that feel okay? So again, it's just like, as long as you don't try to bite off more than you can chew, it's just like, okay, I need this point, I need this slope. This is how I get the point, this is how I get the slope, and don't try to do too much in one step. Use your previous answers to just like... Oftentimes they're going to try to give you some time savings by like taking what you just did and then like using it to do the next step. That's not uncommon. Part C then says, write but do not evaluate an integral expression that represents the maximum value of g on the interval from 0 to pi. Justify your answer. Notice here that it's a closed interval, so we have to do that closed interval test again. So we have 0 to pi. So we care about where this was for g. Yeah. So I need where the first derivative is equal to 0, or where the first derivative does not exist, or it could be g of 0 or g of pi. So if I take the first derivative and set it equal to 0, I'm going to be using this guy right here. Oop. Did I change that? So far, so good. To solve this equal to 0, I notice they have a product of two functions set equal to 0. So I can apply like the zero product property, just like you'd get when you factored a polynomial. So on the first one, if I divide both sides by 3, I get just the square root. And I square both sides. And then I subtract 4 from both sides and then divide by 9. And at this point I can stop because I realize there's going to be no solution to this. How do I know that? Can't take the square root of a negative, right? So I have no solution from that part. Where is cosine of x equal to 0? Pi over 2. Yep, but I don't need to consider 3 pi over 2 because remember, we're only on the closed interval from 0 to pi. 3 pi over 2 is correct, but I don't need to worry about anything other than the stuff in between 0 and pi. So pi over 2 is my only spot. Does that feel okay? All right, where the derivative doesn't exist. If I look at g prime, the only way this would fail to exist is if the stuff under the radical is negative, right? But that can't happen because sine squared is a positive number, 9 is a positive number, and I'm adding that to another positive number, 4. So there's no way to get a negative under the square root. So I know that there's no solution to where it doesn't exist. So all I really need to check are these 3. Does that feel okay? So g of 0, g of pi, and then g of pi over 2. Well, we did g of pi already, right? We did it back here. Oops, sorry. We did it right here. So we know that. So we know that's 0 already. That's nice that I didn't have to redo that. G of 0 is going to be f of sine of 0, which is just f of 0, which we already did. That's just 0, because it was the same thing as g of pi. G of pi over 2 is going to be f of sine of pi over 2. Sine of pi over 2 is 1. And I know that this is going to be greater than 0 because the 4 plus sine or plus 9 sine squared is all positive values. So it's always going to be above the x-axis. Everybody agree with that? So anything I integrate underneath that is always going to be a positive value, right? So I don't care what it is. In fact, it says write the expression but do not solve. So it doesn't actually want me to take the integral of this thing. It doesn't care about that. I just am going to note that it's greater than 0. And because I know that is the biggest of those possibilities, I know that is my maximum value then. Does that feel okay, Alex? And again, the computation wasn't too bad on this if you knew what to do. The roughest part was probably solving G prime equal to 0 algebraically. But once you realize that it's just a zero product property, the two things you're left to solve are relatively easy if your trigonometry is okay. If your trig is rough, that is what it is. But absolutely. That feel okay, everybody else? Was I going slow enough through that in enough detail? Michael?
I have a question.
Yeah.
I don't remember what number it was, but it was the integral of using a sine or a cosine of 3x. It was the most recent.
Okay. Let's just take a look at the questions here real quick. This guy right here?
Yeah.
Okay. Shall we do it? Okay. Okay. So when I see this, I see a composition of two functions, right? I see the function 3x that's composed inside of the function cosine x. Probably a u substitution problem. So the u I'm going to pick is going to be the innermost function. Is typically what I want to do. If I do the derivative of u, I get du dx, and then I get 3. Right? I treat that kind of like a fraction. That's bad math, but that's the easiest way to think about it. I can just kind of multiply the dx over. But I don't have a 3 over here. I just have a regular old dx. So I'm just going to divide both sides of this equation by 3. So my dx is going to equal du over 3. So if I make my substitution now, in place of 3x, I'm going to put a u. And in place of dx, I'm going to put du over 3. Now I know I can pull that 1/3 out front of my integral. And really what I'm left with integrating is just the cosine u du. The antiderivative of cosine is sine. And I'll have my plus c at the end. And then my last step will be to put the value for u back in. And that should be my answer.
How would you just know that you
So when I looked at this, I see a composition. Yes, it is the reverse chain rule. So again, if you remember, we have the derivative of f of some u is going to be f prime of u times the derivative of u. So that's what we're doing here. If we want to integrate this now, we find the u, and then we find its derivative, and we make that substitution. Is that?
Yeah,
Yeah, well, I mean, here's the thing. you have an antiderivative rule for cosine of x. As soon as you see that there's something inside of that antiderivative rule, that's how you know it's a u sub, right? It's not exactly your antiderivative rule, but it's like a composition of something with your antiderivative rule. That should scream to you u sub. Is that, Michael?
So with compositions, would you always use u substitution?
Always, probably. The exception might be if you have like an absolute value, where we know for those you have to like break the absolute value at where it becomes positive and negative. Like you use the piecewise definition to break it up.
Yeah, you do.
Sure. So that was just an aside. All right, so just make one up here. All right. I apologize if this doesn't work great. We'll do that. So this is the integral from -4 to 4 of the absolute value of x squared plus 4x plus 4. Everybody's okay there? Oops, I don't want to do that. I'm going to make that x squared minus 4. What was wrong with the previous one? Yeah, it was never negative, right? So you just drop the absolute value and you're done. That's rather uninteresting. This one now is better. So if I think about this, I know the absolute value of x minus 4 is going to be x minus 4 for some, for some x's. And then it'll be negative of x minus 4 for some x's, right? So what I need to find out is when is x minus 4 less than 0? Or conversely, I could ask, where is it greater than 0? Everybody's okay with that? For a quadratic, I think the easiest way to do is, or the easiest way to approach this is to think about it graphically. Does x squared minus 4 open up or open down? Opens up. How do I know that? Leading coefficient is positive. Everybody agree that this is going to be a u rather than a hill? Okay. What are the x-intercepts for x squared minus 4? 2 and negative 2, right? That's where x squared minus 4 is equal to 0. So basically it looks like that. So where does it need to be negative? Between negative 2 and 2. And where does it need to be positive? When the absolute value of x is greater than 2. Or you could say less than negative 2, less than or equal to negative 2, or greater than or equal to positive 2. You could write as 2 separate, and that's fine. So far, so good? So we're going to need to break this up. So from -4 to -2, it'll be like that. Then from -2 to +2, I'll need the negative of it. And then from +2 to +4, I'll need just the regular again. So far, so good. Now, each one of these pieces is easy to do the antiderivative of, right? So that's going to be x cubed over 3 minus 4x. And then I'm just going to pull the negative. Well, let's distribute it through. It's going to be yucky not doing that. Yes.
How did you pick like the balance for the like,
So basically, if I think about the graph, this chunk is where it's above, this chunk is where it's below, and that chunk is where it's above. So every time it switched, where it was above and below is where I had to break my integral. Is that what you're asking?
Yeah.
Okay. So yeah, that's what I'm doing, is I'm just thinking about, because when I do the absolute value of this stuff, that needs to actually be the opposite sign of what I would get when I integrate it. And then from here, it's just like an annoying grind it
So how
out.
does that test from the calculator? If it's not like a multiple choice answer, like above this, that, it was like that.
I would say you should plug them in, and then you could stop. But I would give a question like this, I would give you on the calculator section anyways, because quite frankly, the numbers are too annoying to plug in to expect you to do it by hand. And at that point, I would expect a number if you have a calculator.
And then you would have to do like both the times.
Yeah, so the way I would do this if I have a calculator is I'm going to type in x cubed over 3 minus 4x into like y1. And I'm just going to do like vars, y vars, function y1, and do that of like y1 of -2 minus, and then vars, y vars, function y1 of -4, right? And then I'll do minus, and I'll do a parenthesis. And I guess this way, I guess if I'm going to type this into my calculator, I would really think of that, so I don't have to muck around with a second one. And then I'll do like y2 minus y of -2. So I'm going to take advantage of this kind of stuff so that it's way less annoying to like try to muck around with all of these things. I can just like the calculator do the grunt work for me. And just let it, So even here, even if there's a calculator question, I would say you can just say equals 32 or something at the end. You don't have to show me, waste a bunch of time like writing that stuff out and doing that by hand. And I think from the setup that I gave you guys for test 5, all the integrals are in the calculator section, where I would expect that, like you're doing that kind of stuff at the end and not spending 20 minutes writing it all out and like cubing things on your calculator and then dividing by things. Blech, what a mess. Michael.
that last one, can you get the end when you're plugging in the numbers in 32? Can you just put it in like when you get an integral?
Right. So again, as a I would do both. Like to check this, you could do integrate -4 to 4, and you could do was it math number absolute value x squared minus 4 dx. So I would do both to make sure that I did my antiderivatives right, or I broke this problem up in the correct way. But yeah, every single problem that's a definite integral can be checked on your calculator. Now, on the test expectation is that you're showing, your general antiderivatives, and you're showing some work. If you're doing a u substitution, you're declaring your u and showing me what like du is and all that kind of jazz, and plugging plugging it through, but you'd be crazy not to check it on your calculator to make sure that, that the number you got when doing y1 minus, y1 of whatever minus whatever isn't the same thing coming out if you just type in your calculator and press enter. For sure.
You do like a hard indefinite.
So sure. Let me think here for a moment. Let's do this. So it's indefinite because there's no bounds. When you look at this, what should you think? Should think U sub. What did you see that indicated to you that it should be a U sub? Yeah, it looks like a composition. There's an x, there's a function inside of the square root, right? So the natural choice here for our U would be the stuff inside the square root. So if I do the derivative of that, I get 5. Everybody's good there? So I can, again, treat this like a fraction. Oops. So I have that. And then I don't have a 5 anywhere over here extra, so I'm just going to divide that over. And here's the problem, though. We have our 4x plus 5, and we have our dx, but what don't we have? We don't have anything for this 2x. Now, the 2 is not a problem, because I can just suck that out front, but the x is. The trick to deal with this x is I'm going to make a second substitution. I'm going to rearrange this equation for u so that it's in terms of only x, and then make a second substitution. So if I solve this for x, I'd have u minus 4 divided by 5. And now I have my substitution for x. And everything is in terms of u's. Is everybody okay with the substitutions? Okay. I would next take all of my constants out front. So I can take 2 over 25 out front. Do you guys see where the 25 came from? I have 2 over 5s. Everything is multiplied together. And then I'm going to think about the square root of u as u to the 1/2. Everybody's good there? And I want to do that because it allows me to distribute that u to the 1/2 in.
Did you lose that 2?
Did I lose that 2?
No.
So this 2 is that 2, right? I just pulled it out front of the integral. So when I multiply fractions, I multiply the denominators together, that's the 25. Multiply the numerators together, that's the 2. And since it's a constant, I can just pull it out front the integral and ignore it. Just going to hang. It's going to ride shotgun here the rest of the way, but I'm not going to touch it again. So far, so good? Now that I've done this, I've gotten this into a form where I can do my antiderivative rules, because now this is just a power rule antiderivative. So that's going to be like u to the 3/2 plus 1 over 3/2 plus 1 minus 4 times u to the 1/2 plus 1 over 1/2 plus 1. And then I have my plus c at the end. So that's 2 over 25, and that's going to be u to the 5/2. And it'll be like 2/5 there, minus 4u to the 3/2. And that'll be like, actually that'll be like 8 then. And you could do some more distributing or whatever, but like,
If we got like the first part where it's just like u plus 1.
no, because you need still to do one more thing. What's that one more thing that needs to be done? You need to put the x back in, right? So 4x plus 5's got to go back in. Or 4 plus 5x, excuse me. And this is nastier than something that I would give you on a test or whatever, but like you asked for a hard one, and this is like got yucky in a couple of places algebraically. You had to do that second substitution. That's the trickiest one to realize that that's something you can do. And it really, that second substitution is a trick that really only comes up with radicals. If this was like x sine of 3x plus 5 or something, you're out of luck there. Like u substitution isn't going to get you to the finish line on that one. It's only because when I put the u in underneath the square root, I can make it a fractional exponent and then distribute it through the polynomial and get to a place where I can just do power rules to anti-differentiate it.
Will we ever have to do like a double u substitution?
I would not ask you to do that.
Okay. 2 channels.
Yeah, I would not ask you to do something like that. I think that's harder than what needs to be done here. I think that's beyond the scope of like a BC calculus question, to be honest with you. Yes, Finn.
What was one of the other
So like you'd be given either like a graph or a table. So like, if you're given a graph, like whatever, and then just say like, we have some if you're doing a left or you're doing a right Riemann sum, you're basically just like doing one of these guys, right, and finding the areas of the rectangles. So you're using like the right height. So you'd like read the value from the graph and then just have like whatever this delta x is times like f of, like 1. And then you do the same thing. Just add them all up. Should be really easy, right? Like if it's a table, it's the same idea, right? You're just reading the x values or the heights from the table, and you're using the distance between the x's as your delta x, and you're just making rectangles or whatever. Is that good enough? Yeah, it won't be anything like, it'll just literally ask like, here's the function, calculate the right Riemann sum or the left Riemann sum or like a midpoint Riemann sum or a, trapezoidal or whatever. Like, I'd give you the formula for a trapezoid if I asked you to do that. But it should be pretty straightforward. especially if I'm going to ask you to do it without a calculator, right? I think it was on the note. Was it, which section was that in? Was that calculator or no calculator? I can't even remember. Oh, it is calculator. Oh, yeah. So the numbers should be fairly easy to deal with even so. Does that work for you? As long as I'm like comfortable doing a Riemann sum, I might do like 1 or 2 practice, but they should be pretty simple to get the hang of. And we did a fair bit of practice at the beginning, right? That was like 5-1. It was like all doing Riemann sums. How do you guys feel? Is this feel like it's coming together? Getting some of the question marks filled in here a little bit, I hope. Okay. Do you guys have other stuff for me? Do you want to talk about? Yes.
It's just like a different.
Yeah, go for it.
For the homework quizzes,
Mhm.
are they due before class or like the day of class? Like the day you assign?
Ideally, I'd like you to do them like the day they're assigned, but you know, like anything else in here, I'm pretty flexible on due dates. But I try to have one every time we do a new lesson. I try to have one that includes, you know, something from what we just did, plus a review idea, you know, like 1 or 2 questions from first semester, really, just so that none of that stuff can slip away too far on you. So I think, what we've done, I think I've assigned 6 of those guys. So if you have, you know, if you want to check your My Notre Dame or whatever, if you're missing a couple, keep going, you know, go back and do them. I put no due dates on them so that you're not locked out from doing them. So if you're behind, try to get that knocked out here in the next day or 2. I'd like ideally to have all these done before we take the test at the minimum. But I understand like stuff comes up or we forget or whatever. It's not that big of a deal. But like, you know, if we did section 5.5 and I have a homework quiz from 5.5, by the time we meet for the next class, ideally I would have liked that done. But, you know, it is what it is. I get that sometimes like we're traveling for sports and like forgot about it or like my tablet died or, you know, it's not the end of the world. So is that, everybody feel that's reasonable there? Do we like this homework quiz format? We're just having like these, squeezing in some more multiple choice practice anyway. Yeah. I know you probably miss your partners. But yeah, so that's, what else do you guys have? Do you feel okay on the format? What to expect come the test time? Yeah, Michael?
Questions, just like the ones like number 5 with like the derivatives, like the number 5.
Yeah.
Going back and forth like the picture of the derivatives. I think that's like the first part.
Yeah, that's probably conceptually the hardest thing is to deal with. Like, I'm doing these second derivative tests on this integral function where the first derivative of this is actually just the function, or the second derivative is the derivative of the graph, and like making sure you are comfortable with like where I am in the problem and like what I can do to show this, because most of the time you don't have an equation to take a derivative of, right? All you have is like this picture. But
When you're doing like the tests to like use one to pick the values and the other one to actual plug them in.
yeah, so like when I'm looking at the first derivative of g, I'm actually just using the graph for f. Yes, yeah, and that's a very common, like I picked this because this is a really common FRQ format is to like give you the graph and set up as an integral function and have to deal with like first and second derivative tests using this, because it really kind of conceptually makes sure you understand like what it is I'm looking at, how to use, like the fundamental theorem of calculus to peel off the integral and left with just the function. And if I take a derivative again of that, now I've peeled off the function. I'm looking at just like the derivative of that function, so I'm just using the slopes of the graph provided or whatever. But yeah, I mean, this is conceptually, this is some of the, like most layered questions that we're going to see are these where you're like moving through from like integral to function, to derivative of function, where you're not actually given like an equation to do any of it with, right? You have to like use the picture. So yeah, I think that's why I gave you guys all the extra practice here and gave you the my worked out solutions for it, because I think this is a, like an important concept, and I think really helps tie together a lot of ideas from first semester. Because that's what you will see in the FRQs is you'll see stuff from potentially like the first test, the third test, and like the seventh test all in the same question, and just getting comfortable at like how the information from one of these topics ties together with something else, or how to move like from one presentation to another, I think is very common. So we just got to get comfortable kind of doing that. Paulo?
Are we on schedule?
Oh yeah. Yeah, I think we're in a decent spot here. I wouldn't have given you the extra day here if I felt like we were behind schedule or anything. I think we're in an okay spot. And there's some places where there's some stuff that I can just do less of that isn't expressly A-B stuff that I think is like something we should do in this class, as many of us will be going on to take a college calculus class, next year. And I think that foundation is really helpful. But there's other stuff that I don't really have to do this right now if I need the time. But I think we're in a good spot. We finished first semester right where I would expect us to, which is good. Yeah, Michael.
In this class, how do you normally do on the AP?
Well, it's hard to phrase that because, I think that by the time the AP exams roll around, I think there's some seniors that are just I'm done with school. I don't think I can get better than a 3 or a 4, so I'm just not going to even try at all to get a 3 or 4 and end up getting 1s and 2s. I think the students that prepare well, that prepare I'm going to try to do as well as I can, 3, 4s, and 5s are definitely doable. Kids get 5s every year. That's not an impossible thing to have it happen at all. But because everyone is required to take the test, your scores are kind of deflated because of that. But based on what we do in class and what we get through and how well we cover it, and really how well you guys perform relative, I think that no one in the room is incapable of getting less than 3. Every single one of you guys can get at minimum a 3. I think that is wholly doable.
The 3 is a 25%.
It's probably a 40, but it is 100%. That is so doable for every single one of you if you prepared well. Now, I would say at least half of us 4s and 5s are wholly realistic. Wholly realistic. But you have to prepare. like once school ends and you have a week or whatever before the AP exam, like you have to study a little bit every day. I know, which is hard, right? Like you get to the end and you're like, you know what? Like it doesn't really matter that much. There's parties and like this thing or that thing or the other thing. And like, I'd rather hang out with my friends. And it's like, my best advice to you is just like, do it before you go out.
Do most schools like offer like credit for this test?
I think it varies from institution to institution and depends on your major as well, I think. You know, like if you're going to be an engineering major, they might want a 5 at like the University of Michigan. But if you're going to be like a humanities person, I think that I would be shocked if they didn't give you your math credit for a 4 on the AP exam, regardless of the institution you're going to. So just, I think it varies a little bit between where you're going and like what your major is. Does that make sense? I wish I had a better answer for that. But again, we should have plenty of time at the end. We'll do some like full-on practice portions so you get a feel for like what this is going to look like, and we'll time it so you get a feel for like the timing of it. But in general, like, you know, for the multiple choice sections, you should be, you know, like 2-ish minutes a question should be kind of what your internal timer is like. Looking at the little homework quizzes, seems like you guys are doing fine there. Most of you guys are finishing kind of in that 10-minute range on those for 5 or so questions, which is about the right timing. So that's good. The FRQs are hard, you know, like because it's all mixed together inside of one question. Sometimes it's not always just upon reading it obvious, like, what am I supposed to be doing with this? But you have a lot more time for those. Michael?
Is it like, I forgot, like the test, like break down how to do it? Is it like no calculator, multiple choice?
Yeah, so there's a no calculator section for both multiple choice and FRQs, and there's a calculator section for both multiple choice and FRQ. So there's 4 sections to the test. And I think, do I have that all still up here somewhere? I know I've made those in the past. Let's look real quick. Okay, so I have the test date up there. I don't have the exam breakdown. I'll get that and put it in an announcement so you can kind of see the order and how much time and questions and everything are on the different parts. So I think your last day of class should be around the 7th. I think that's when senior grades are due for us as teachers. So it'll probably be before that a little bit.
They were saying May 1st.
Okay.
They were saying May 1st.
Yeah, so you'll have like, that's a late exam date for us.
Yeah.
Where you're still like almost 2 weeks maybe between the last day you'll see me and then, so that's one that I think is harder for you guys. I'd rather have it like the last day of school. I'd rather have you taking the AP exam because the motivation becomes less of an issue because I can make sure we've been studying in class at least the week prior to it. But if that's something that that's important to you and that's a plan, like I want to do well because I think I can get credit and that's, thousands of dollars that I'm saving by doing that, make a plan, it's much easier to do a little bit every day leading up than try to save it and try to do a 20 hours the day or two before, which is kind of miserable. If you have 10 days before the exam, if you do an hour every day, that's 20 hours of studying. That's incredible. You should feel really confident and really well prepared if you do that. You know what I mean? So it's chip away at it. Don't try to marathon session it. It'll go a lot better. I don't know. What do you guys think? Test day, what are we doing? Thursday?
Yeah.
Okay. Let's plan on that. If you're a Kairos person, you're going to be gone. Unless you've spoken to me about wanting to do it beforehand. Yeah, like before you leave today. Somebody talked to me about wanting to do that. Did we? You changed your mind? Okay. I forgot to, wherever it was supposed to go, I forgot because you forgot to email me as a reminder. So I did forget that too. That's fine. You can do it when you come back. No big deal. If you're going to be gone on Kairos, though, can you at least have a planned test date that week you're back? So shoot me an email. Let me know what your plan is as to when you're going to take it if you're going to be gone on Kairos. And it doesn't have to be like, the day you come back or anything, but hopefully sometime that week I'd be totally fine with that and be super happy to have it done sometime that week. Okie dokes.